So I want to talk about the scope of locality-preserving unitaries implemented in various ways. So this is the plan or the goal of the talk. So at the very bottom of the class, there is a unitary circuit. And the next class will be what's so-called the QCA. And there's something more to it. I don't know how to call it, but there's something more to it. In this paper, we called it MQCA, but you don't have to stick with it. Although I'm only going to talk about this subject. This will appear at the very end of the talk. We will start with the bottom and then build up gradually. So why do we talk about unitary circuits in the many-body context? Let's just remind ourselves why we do that. The most compelling motivation for me comes from the Matt's work in 2005 or 4, a so-called quasi-adibody continuation. So, in topological phases, when you talk about topological phases, you want to start with a definition as a mathematician, and the conventional definition would be you have some family of Hamiltonians. It doesn't have to be a single family, a single parameter, but for the sake of simplicity, I just write it as a single parameter with some local perturbation. And then you want to demand that the energy spectrum has an energy gap from the ground state. So pictorially, the ground state energy stays at zero for the entire interval, and there is some energy gap above it. And all the excited states, we don't really care, as long as this is empty. And in this case, what you want to think about is the ground state projector, parameterized by this parameter S. And you can think about the evolution of this projector along this path. So you can think about this differential. And it turns out that this has some Schrödinger equation-looking equation that looks like this. And the main point in this work is that this evolution generator has a locality. It's a sum of local terms, pretty much as a local Hamiltonian. Although, since we're talking about the projector on the space of Hamiltonians, this is really not it may be a misnomer to call it Hamiltonian, but this is essentially a Hamiltonian. There's a specific expression that you can work with, and that's the source of all the nice theorems from Matt. And since this is a local sum of local terms, the evolution itself, the integral of this equation will give you some unitary generated by this sum of local things, and that corresponds to the local unitary circuit. It doesn't have to be a circuit, but circuit is just a discrete model where this is happening. And from this from this work, we tend to think that topological phases is just an equivalence class of states related by the finite depth quantum circuit equivalence relation. That's the source of the unitary circuit in the topological phase.
Is it conceivable to consider situations where the lowest energy and the first excited energy is periodic in S between 0 and 1, but the rest is not? So in full theory, it's non-periodic, but only the first two eigenvalues, the physics.
Oh, yes. In that case, you have so this ground state projector is well defined. So it defines a bundle of the parameter space. So you can talk about the physics there. I believe.
But there will be some Berry phase associated with it, and you have to take care of that.
Yeah.
Good.
And then people often talk about the boundary of topological phases, and for this talk, our focus is entirely on the unitary side. I don't really worry about the states anymore. So let's examine what happens at the boundary of a unitary circuit. So everybody would have a picture for the unitary circuit that looks like a brick wall diagram, which is not too wrong, something like that. And then when we talk about boundary, I'm going to just drop them. I'm going to just erase some of the gates on the, say, half plane of the space, and let's look at this boundary region. One theme that keeps coming up from when you first learn topology is that you think about the loop in the space of the space you want to think about. I want to think about the unitary, so I think about the loop in the space of unitaries. But what does that mean? You start with some base point, and base point for unitary is the obvious one, identity. So I think about the loop in that family of unitary circuits that comes back to the identity. In the circuit language, that means that you have some unitary that implements identity, but you have implemented that unitary through some non-trivial path. But what does that mean in this picture? What does that imply when you open up the boundary? On the far left side, you have obviously you have the nothing, so you have identity, the base point. On the far right, since you have a definite light cone here, the action of the unitary circuit on the far right is the original one, which is identity again. So something non-trivial is happening possibly at the boundary. But is that action well defined? To some extent, yes. Well, obviously it's not. I mean, I could, in a naive sense, it's not, because I could have dropped less gates or more gates. That ambiguity is always there. But whatever I do, if I have some two different droppings, and everything here is the same, then if I look at the difference, then everything on the far right will cancel off. Everything on the far left, there's nothing to cancel, but it's anyway empty. What you're left with is something acting on the boundary that consists of these blocks. So you have, this is going to be a circuit at the boundary. So if these were d-dimensional objects, if this were a unitary circuit in d dimensions, then at the boundary we have a circuit in the one dimension lower. So whatever action there is, the action here, alpha, is well defined up to circuit in d-1 dimensions. So I started with a loop in the d-dimensional. I started with a loop in the space of all unitary circuits in d dimensions, and then I ended up with an object in one lower dimension that is defined up to circuit elements. Now, at this point, you might wonder, oh, what's that? What that can be? What can we abstract this situation a little bit? What's the property that defines this alpha? Well, alpha is going to be acting on some operator here, and will conjugate by some gates that's left over. So it obviously preserves locality. And it's defined up to circuit. Is there anything left? Famously, there is something left. It is the group of all locality-preserving unitaries up to circuit. So, okay, let me define it. Matt also defined it once in his talk, that it is so, yeah, QCA is just a fancy name whose terminology I don't really endorse, but for historical reasons I cannot avoid. just the locality-preserving automorphism on the operators, like big unitary that happens to preserve locality. And I wonder about the group of all QCA modulo circuit. So loop in the one-dimension higher unit circuit lands into this object in one dimension lower. And this object is non-zero. The most easy example is the translation. So imagine a now two-dimensional situation. Now, well, something like this. And then you consider the swap gate. Just swap the two degrees of freedom here and there, and you go on a circular fashion. In the bulk, you go around the loop. Any degrees of freedom will return to its original position. But at the boundary, since you are dropping something, you induce a certain flow due to that translation. And this flow is not a quantum circuit at that dimension. So this is a representative of the in this quotient group. So this is one way to think about this hierarchy. We talked about the unitary circuit, and then at the boundary, we actually enlarge the scope of this locality-preserving transformation.
Is there a backwards map?
Backwards map? Oh yes, yes. So yeah, given an element here, you can construct a one-dimensional higher loop representing that element. Okay, so now I want to talk about a little bit, one step further using measurements. You may wonder, that sounds weird. Measurement is not a unitary transformation in any sense. It's a projective. What are you talking about? But there's something to be done. I mean, there's some story to be made. First, let's review what measurements can do. If you have studied any measurement-based quantum computation, then you would know the answer. You can do anything. But let's review that. How that's done. It comes from the old idea of gate teleportation. You know how teleportation works. There's an incoming qubit or any qubit, and you prepare a maximally entangled state on an ancillary system, and you make a measurement. Then, based on the measurement outcome, well, the outcome is always random, but there's some simple correction you can apply in such a way that this is exactly like this. So this qubit is now teleported to the third one using ancilla. You could insert any unitary there. So in other words, you prepare a Bell state, the maximum entangled state, and you apply a unitary of your choice to one party of that Bell state. And then you make a measurement as if you are doing the teleportation. And the end result, what you get here, your original psi is teleported with the unitary applied. If you look at the diagram, that's trivial. I mean, it has gone through this U. Measurement outcome can be random. Well, it is random, so you may have to apply certain corrections there. But modulo that correction that is deterministic upon this measurement outcome, you have applied this gate. So using this technique, you can basically do anything. This preparation step can be done by measurement. This Bell measurement is a measurement. So modulo this correction step, you are doing everything using measurements. Measurement is destructive, but using ancilla, you're achieving the unitary transformation. Now, there's one thing I want to talk a little bit in depth. Namely, the measurement here is always random. you learn nothing about the state. That's a requirement. It's just an uncertain principle. You shouldn't be disturbing the underlying state by your measurement to achieve this unitary transformation. So your measurement should not learn anything about here. And the one way to learn nothing about your system or from measurement is that when measurement is 50-50 random. And indeed, restricting to the Pauli stabilizer state, suppose you have two anti-commuting observables, A and B. So there's minus sign there. And suppose you start with some eigenstate of A. And then you measure B. What happens? In that case, the probability of measuring +1 will be this. But since it is stabilized by A here, so conjugating B, so whenever you're measuring the anti-commuting pair of some stabilizer of the original state, then you are always getting 50-50 random outcome, which is the case here because the Bell measurement you're making has an anti-commuting operator with the prepared Bell state.
May I ask a stupid question?
Yeah.
If I see these diagrams, for you the state preparation is also called measurement, right? Because in some sense you prepare an entangled state. Just for, what is measurement, right? On your diagrams?
Oh, it is a measurement in the sense that, say, the Bell pair is, +1 eigenstate of this. I'm sorry, it's the image of
projection onto the eigen. Yes. Of course. Yeah. Okay.
You can deterministically prepare that.
But picture-wise, it's also nice. This thing is a measurement, and this thing is a measurement.
Right. Yeah, you are confusing about the time coordinate there. But it's not exactly symmetric because of this correction operation. So the origin of this unitary can be understood from here. Let me define a unitary U. Like this. Why is it unitary? Well, if you square it, they cancel. They are 1, so this is 1. So U is a unitary. And indeed, if you apply U to the original state here, then you can show by a simple calculation that it is indeed eigenstate of B with eigenvalue of 1. So effectively, the post-measurement state, post-selected on the +1 outcome, can be achieved by applying U on the original state. And that can be thought of as the origin why you could have implemented unitary using measurements when you learned nothing. And this is what's happening on the Floquet code. Let me talk about that, which Dave has spent an hour, but maybe it's okay for me to repeat a bit. So we have a 3-colorable lattice. The numbers denote the color of the cells, and the qubits are placed at each vertex. And the code protocol is going through the measurement schedule, where you measure operator, say ZZ, along the along the edge that connects the 0. In the next round, you measure the XX along the edge that connects the 1 cells. And in the next round, you measure the edge along that connects the cell color 2, and so on. It goes periodically fashion. And every measurement is also that zero knowledge measurement. So, right. In the paper with Dave and Z and Roger, we named it as a reversible measurement. This is nothing but when this happens, when the measurement outcome is completely random, so the post-measurement outcome could be achieved by a unitary, then we called it just a reversible measurement. But there are too many measurements here. We want some grouping, some nice grouping, so that we can understand it better. And for that purpose, we can think about locally reversible measurement. This is a name may be fancier than needed. What's happening is this. So think about the stabilizer group at time step t, and you consider the stabilizer group at the one step later. There could be some intersection that we don't mind, but by definition of locally reversible measurements, we demand that there is a choice of generators for this stabilizer group. In other words, the choice of measurement operators that you choose in each round in both sides, such that they anti-commute for the anti-commuting pairs are perfectly paired up. And I demand that each generator is local in space. If you could find such a basis, then we call the measurement to be locally reversible measurement. Right.
So does reversible refer to the encoded information rather than, I mean, literally you can't reverse a projection.
All right. So reversible means that reversible is chosen because the effect of measurement could be reversed. Effect on the encoded information. Right. And local just means that reversion can be done in a local fashion. And technically, that means that we are going to measure certain pairs of generators in such a way that the pair only sees the other one in a local neighborhood, nothing else. So if this happens, then the transition from time step t to time step t plus 1 can be implemented using measurements. Using unitary. So we designed the measurement circuit in such a way that the overall effect on the encoded information ends up being a unitary of small depth unitary circuit. That's what's happening in the Floquet code. The difference between this unitary picture and the measurement picture is that in the unitary picture, you learn nothing. You literally learn nothing. So you cannot do error correction there. There's no central information and so on. But using measurements, you learn something, and that something is only tailored to the noise part, not the encoding information part. So that's another way to think about the Floquet code. And why am I telling you about this locally reversible measurements when I talk about the locality-preserving unitary? Because it can do something interesting that is otherwise not possible. So here's a simple example of translation. I told you from like a picture I raised here that some two-dimensional circuit, a unitary circuit of small depth in the two-dimensional bulk can induce a translation along the boundary while it achieves identity in the bulk. And I said that translation is not a standalone quantum circuit in one dimension. But here I'm going to show you that using measurements, the translation becomes possible. Just a teleportation, actually. So here are my qubits. And say I measure x in every other qubit. So my encoded information, my logical piece, will be only on the odd indexed qubits. And then how does the teleportation protocol work? You prepare the ancilla, and then you make a Bell measurement, but the compressed version is just to do this. So since this is an X measurement and ZZ measurement, they are anti-commuting pair. The measurement outcome will be random. You are not destroying the encoding information here, but somehow spread it temporarily. And then you measure this qubit in X basis again, so that this qubit is now teleported like that. This measurement is random. This measurement is again random because the X and Z here anti-commute. Once you achieved one translation, then you can go back to the original configuration by teleporting once again. So you make measurements like that. Yeah. And then I should have started lower here. So you are implementing a translation in this way, just iterated teleportation.
Is the information only stored in every other qubit?
Yes. Yeah. So yeah, this is ancillary. And this is information. So yeah, measurement did something better. But thinking about in terms of this unitary, effective unitary induced by this measurement, that mimics the action of this measurement, what happened was that these information qubits are translating to the right, but at the same time, the unitary teleports moves these ancillary qubits to the left. But the ancillary qubits are in the product state that happen to be translation invariant. In other words, the unitary did implemented alpha and alpha inverse, this acting on the information qubit, and that was acting on the ancillary qubit. But the ancillary part was just remain invariant. It was an eigenstate of this alpha inverse. That's the underlying reason why measurement could have done it. You had an ancillary system that happens to be in the eigenstate. And this stuff may have been an old story for some of you, but the one new piece I want to tell you is that actually this happens for all QCA, at least in the Clifford category, at least in 3 dimensions. I believe it holds for every dimension, but there's one technicality which I mentioned. So let's understand that. That will be the goal of the rest of the hour. And for that purpose, so now the goal is kind of clear. We want to find, given the Clifford QCA, or any other QCA, we want to find an eigenstate of this alpha. And that eigenstate should not be too long-range entangled in a rough sense, that because we want to be able to implement this using measurements only, that involves only local. So the underlying eigenstate of this alpha must be prepared using local measurements. That's my only criteria, only condition I want to impose. So how can that be done? The space of QC looks quite complicated. I told you it is non-zero, but I didn't tell you how large or small that is. There's a, well, so that comes the result of this paper, which I wanted to talk about. So there's a, I'm going to give you one definition for what is called invertible subalgebra, which will be important to find an eigenstate of this alpha. So now put all the measurement or circuit stuff aside for a moment and just focus on the algebra side. So what I'm going to want to talk about is just the usual operator algebra on lattices. So how do you construct the operator algebra? You have a matrix algebra for each qubit or qubit, and then you tensor product them, and you take a thermodynamic limit. That's it. And there is some, now every qubit is embedded in some metric space, and by which we talk about the locality. And invertible subalgebra is a subalgebra of that, the full operator algebra on my lattice system. And the definition is that let B be the commutant of my interested algebra, where the commutant is taken relative to the full operator algebra on the full lattice. And then the condition is, if you give me any operator in this full matrix, well, it's not matrix algebra, but I keep using the notation mat because it's, did you have a question? Yeah, it's built out of matrix algebra in a way.
Do you include essentially non-local operators in your full operator algebra?
No. So no. Well, yeah. So the infinite tensor product of matrix algebra doesn't make too much sense. So what you do is you build up a directed system for increasing sizes. And you take an inductive limit, and the element there has always a finite support. There's nothing infinite. Everything else is eventually it becomes identity at the far away. So for that reason, people call this as a local operator algebra. Right. So the condition is whatever operator on the mother algebra you give me, I should be able to write it as a sum of, in this form, where A is in the algebra you're interested, B is in the commutant. But the important requirement is that the support of AI and support of BI, they must all be in the small neighborhood of support of X. This is important condition, the most important condition. So put differently, so you consider the abstract tensor product of the interested algebra and its commutant. It is not, this tensor product is not the same as this. I just made up a so-called, well, maybe I call it exterior tensor product of the two. And then I consider the multiplication map into the mother algebra. Well, they were subalgebra, so they have a multiplication map, like A tensor B is now mapped into AB. And the equivalent condition for this is that this map has an inverse that preserves locality. So A and B have notion of locality. Every element of A is an element of this mother algebra, which has a notion of metric, so you can talk about the distance between two operators and so on. B also has that property. This obviously has a locality property. And the inverse, whatever you give me here, I should be able to express it there while this locality preserving property is obeyed. So I have an isomorphism between the two. And that's the definition of invertible subalgebra. Why is it invertible? Why do I call it invertible? You may wonder. Because I call it invertible because if you think about the set of all these subalgebras, then they form an abelian group, where the trivial element is the full algebra or the trivial algebra. Abelian group modulo, whenever this isomorphism so I identify any subalgebra that happens to be isomorphic to the full operator algebra in some locality-preserving map, then I declare that as a trivial element, as in the with construction. So, and this becomes a normal subgroup of this under tensor product, and the quotient becomes an abelian group. Now, the one theorem is that this group, which I call Brouwer group, because the construction is pretty much similar to the usual Brouwer group of a field, all the algebra representations over the field, is isomorphic as a group to the group of QCA in D+1 dimensions. So instead of, I skipped a major step, of course. I just gave you a definition, and then here's a theorem statement. But the point is that the group of all QCAs modulo that you don't want to think about, the UCA modulo unitary circuit, and shifts, that object that lives in the D+1 dimension is isomorphic to this rather abstract-looking abelian group of algebras in one dimension lower. They're just the same thing.
So your wiggly line is both circuits and shifts?
Circuits and shifts up to blending equivalence.
What?
Blending equivalence?
What?
Blending.
Oh, blending.
Yeah. So it's a little bit coarser, stronger equivalence relation than the circuit equivalence. So instead of thinking about D+1 dimension, now you can think about objects in one dimension lower. So it reproduces the old known result in the one dimension. When capital D is 0, then you're talking about the QCA modulo the blending equivalence relation, and you're talking about the Brouwer group over complex numbers in 0 dimension, just a matrix, which is trivial. And that matches the usual GNBW story. Another theorem, it's a byproduct from this proof, is that for every QCA alpha, there is an invertible subalgebra in D dimension such that alpha acts like this. Can everyone see it? Maybe I shouldn't draw it here. So I think of the D plus one-dimensional lattice as a collection of sheets. So each is D-dimensional, which is possible because it's a lattice. It's not a continuous space. It's a lattice. And then, so on each sheet, there is a local operator algebra, the full local operator algebra. And then you give me an element, x here, and my action of alpha is as follows. You decompose x according to the definition of invertible subalgebra. So you write x as a ai bi, sum of ai bi. Ai is in this a, bi is in its commutant. And then you map this thing by alpha to you leave a piece here, but you toast the b part to the next layer. So the procedure is you give me an operator living on a sheet, you decompose according to the definition of invertible subalgebra, and you toast one piece to the next layer. And the theorem, which actually implies this, is that every QCA, after some modification by trivial moves, like a quantum circuit and blending and shifts, then it becomes just this one. Every QCA is just this. So in a sense, every QCA is a translation in disguise.
The theorem for Clifford QCA or the
No, this is general.
This is general.
Yeah. Strict locality.
Strict.
I have a question. Can you use that to prove properties like area law from lower dimension and pump it up in higher dimension?
I didn't think about that. Not sure, yeah. Well, this theorem is not that deep, so probably it does not imply. Okay, so yeah, this is that. Let me give you one example of invertible subalgebra, because theory without an example is boring. Unfortunately, the example is something I cannot remember. So it's a square lattice. We're working on 2 dimension. There is a Q trait on every edge, and X denotes the clock unitary, and this is the diagonal unitary. And what I drawn is the generator for my invertible subalgebra. This is perhaps the simplest I can write down on the board. And it is a theorem from Mike and Matt that in 1 dimension you cannot find anything interesting. There is no non-trivial invertible subalgebra in 1 dimension, which translates to the fact that 2-dimensional QCA is only as shifts and a circuit. That's it. But starting with a 3 dimension, there is an interesting example implying there's something going on at starting at 3. So remember, you're not allowed to factor out the different pieces. You only can multiply them, add them, and take a dagger of this operator. And that's the operation you can do in this A. And this is yeah. Okay, now let's get back to the original question. How can,
sorry, what's so special about this example? I didn't catch that.
Oh, thanks. Right. So, right, I almost forgot. So, okay, let's, in the mundane operator algebra, it is trivial to write a trivial Hamiltonian. Just project every qubit in a product state. What's wrong with that? Trivial. And one particular nice thing about that trivial Hamiltonian is that it consists of commuting terms, no problem. In this invertible subalgebra example, or actually for all non-trivial example, I believe, if you were forced to write a commuting Hamiltonian, then you must write an anyon theory. There's no trivial Hamiltonian you can write using commuting terms in this algebra. That's
Trivial.
trivial means product state. Or,
Projects the product.
no, so more precisely, any commuting Hamiltonian you write down in this algebra must have a non-trivial selection theory. In the thermodynamic limit, if you have a Hamiltonian, then you seek for the GNS construction for the Hilbert space. And trivial Hamiltonian means that there is a unique ground state representation. For this algebra, if you write a commuting Hamiltonian, whatever you do is going to be non-trivial selection theory.
So just because you have a commutant?
Sorry?
Just because you have a right commutant?
Partly because yes, but well, that's not the reason actually. It's part of the reason, yes. Right.
I don't know if you can, well, what you said means probably you can realize chiral theory.
That's a more stronger statement, yes, but which I believe is true.
Okay.
But the weaker version is that, yeah, and at least you have a non-trivial super selection.
Okay. The non-trivial, what?
Super selection theory.
Super selection.
Yeah. So if you write a gapped Hamiltonian using commuting terms, then the underlying theory must have anyon. I believe that's the character. Well, okay. So just to be precise, what I said is actually a conjecture. What is proven is that if you were forced to write a commuting Hamiltonian using Pauli terms, then you must have an anyon theory. That much is proven. But if you relax the Pauli condition, then it is a conjecture. Okay. Well, at this point, now I can answer the original question. What's the eigenstate of the alpha in 3 dimensions? That is eigenstate of local measurements. And the answer is just a toric code, actually. What happens? Maybe I can use here. So put a toric code Hamiltonian in this, and on every sheet, two dimensions. So the 3-dimensional lattice is a collection of sheets of 2-dimensional planes. And on every two-dimensional plane, I put a toric code. And then it turns out that toric code decomposes into 2 separate theories. And for this over Q treat, the fusion group is Z3 cross Z3. And there are 2 different ways to decompose these 2 copies of Z3. One into the all boson, and well, yeah, it's not even modular. So there's one way to decompose it into 2 copies of modular theories, one being chiral along this way, the other copy along that way. And that decomposition is actually compatible with my invertible subalgebra decomposition. So you put, say redundantly, if you start with a toric code Hamiltonian and then apply that decomposition according to my definition of invertible subalgebra, then the one term describes one chiral theory, the other term B describes the other piece. Now, since I put the every toric code on everywhere, decomposition and shifts is a stabilizing operation. And toric code is preparable by local measurements. Therefore, there is an eigenstate of this QCA in 3 dimensions, and I can implement this alpha piece using measurements. Yes.
Just to connect with your previous use of that picture, when you put a toric code on the sheet, should I think of the algebra of operators that stabilize the toric code ground state? Before you were writing algebras on the vertical sheet, and now you're writing phases. So what's the relation?
So right. So let me just remind you. I wanted to find an eigenstate of this on the invariant state under this QCA. So my algebra is fixed. Algebra is just a full operator algebra. And alpha x on that has an automorphism. And one way to find an eigenstate is that one. You put the toric code state. Our focus is to find the state, not the unitary. And one state is just an infinite stack of 2-dimensional toric code that happens to be compatible with this split shift operation. And that state remains invariant.
But you have to split with respect to 2 subalgebras.
Yes.
And how are those algebras defined relative to the toric code?
So good question. I skipped that part. So, right. In this algebra, you find the Hamiltonian. And that Hamiltonian realizes the one slice of my Z3 toric code. And on the commutant, you find the similar thing, but that happens to be the time reversal conjugate. And together, they make a toric code state. So, right. So why did I have to say that, I'm going to realize every Clifford QCA, not every QCA? The reason is here. The mapping for every QCA, there is a invariable subalgebra in 1 dimension lower and split shift. That holds generally. But it's not entirely straightforward to find such a Hamiltonian in a general invertible subalgebra, such that it is now compatible with my splits. It's rather embarrassing reason. It's not even clear if there exists a local gapped commuting Hamiltonian within that invertible subalgebra, which sounds benign, but it's tricky. It leads you to the question like, given an algebra, can you find the gapped Hamiltonian inside? Local Hamiltonian, strictly local Hamiltonian. Sometimes you have to break the translation symmetry, or even if the algebra is translation invariantly generated, and that complicates the story. But for this example, you can. Therefore, I can say that every Clifford QCA is realized by measurements. Right. Let me conclude my talk just by saying that. Yeah.
Would it have been necessary to project into the full toric code, or if you just use just the terms in this algebra A and just project that one of the factors is in one of the chiralities is the
That's enough. That's enough.
And you can leave the other one.
Yes. Yes.
And you can still do that projection on the one factor as well.
Yes, because they are, you just measure those.
These are still local terms.
Yeah. Right. My solution is a kind of overkill. So I did not talk at all about this. So we started with the unitary circuit, and then by examining the boundary of the unitary circuit, when the unitary circuit implements identity, we find QCA on the unitary world, and which is not implementable by unitary circuit, but if you endow measurements, then by going around some detour, we could implement that. There's another story at the boundary of a measurement circuit. And that's what happens in the Floquet code. So, we examine the boundary of a unitary circuit to find the interesting subject, which is now realized as a circuit in that dimension using measurement. Now it's time to look at the boundary of that measurement circuit, and the scope is enlarged, indeed. And that's the point of this paper. The upshot is that since we're working with a subsystem where the measurements, since you're ignoring some subsystem in the measurement circuit to induce a unitary on the other subsystem, the system that is stabilized by this measurement cycle can be anything. And by choosing something interesting, you may be inducing something interesting at the subsystem, which is precisely what's happening in the Floquet code, it turns out. You are in the Floquet code side, this enlarged subtle thing is like a half-qubit translation or a Majorana translation. We do not know anything about higher dimensional analogs. There must be something, but I don't know how to characterize or anything. So
the M stands for measurement QCA or Majorana
QCA? We intentionally did not spell them apart.
It stands for mystery.
So at this point, QCA is, so far we only talked about just the tensor product local operator algebra. But if you change the underlying algebra, then there's other opportunity. And that's another way to think about this more generalized version. Your domain where the QCA acts is now different because you are talking about the boundary of some interesting state. So depending on obviously, you're talking about the class of functions, and I'm changing the domain, so the class of function is different. So I hope you find it interesting. Thanks.